Good afternoon. This is November the 6th, Math 2413. Just a few announcements here at the beginning of class, and then we'll get started. First of all, Exam 2 was last week. I will upload the grades from Exam 2 either Wednesday or Thursday of this week, hopefully Thursday at the latest. I'm in the process of grading those tests right now. I will upload those to your D2L gradebook. Remember that you can request a graded exam sent back to you by email. Just send me an email, and I will respond with your exam attached to that email. Homework 4 due date. Remember, homework 4 originally was due last Friday, and now it's due this Wednesday, November the 8th. I put those problems on the screen here again just to kind of remind you. I've sent you this a couple of times, so you certainly should have what the homework problems were. A total of 10 problems that I want you to turn in on Wednesday. Remember, please turn those in as a single PDF file and email those to me. And you've got till Wednesday to do that. Online office hours, I'll be available online this week, Monday 8 to 9. Tuesday, note the time difference on Tuesday evening. I'll be in my office, my online office, from 8:30 to 9:30 that evening. Wednesday from 8 to 9, and then on Thursday from 1 to 2. So don't hesitate to come by for help. I'd be more than happy to help you out with any questions that you have. All right, so last time we looked at optimization problems, and we spent a lot of time talking about different optimization problems, max-min problems. And so you have lots of those worked out. You really need to spend some time working on the homework that's to turn in, and then the textbook homework also on those problems. You need to spend some time trying to work through some basic problems. I may send you later in the week some practice problems. That wouldn't be to turn in, but some more practice and basic optimization problems so that you'll have more practice problems going into Exam 3. The more of those kinds of problems you can get through on your own, the better. So the more practice you have on that, and I will try to provide you with that, the more practice you can get on that, the better off you're going to be. All right. So today we're going to look at antiderivatives, and we are headed towards integration. It is our next major topic. And so today we're going to talk about the idea of an antiderivative. This is section 4.10 in your book. Note we've skipped sections, I believe it's 4.8 and 4.9. We skipped L'Hopital's rule, and on numerical derivatives, L'Hopital's rule will be a Calculus 2 topic. And so we're going on to section 4.10 and talking about antiderivatives. Okay, so first thing is let's kind of go back. Remember that if you have a position function, and let's say that that position function's name is s of t. So this gives us the position of an object relative to a zero position as a function of time. Then we've already seen this semester that the velocity function is v of t, and v of t is s prime of t. It's the first derivative of our position function, and you may also see this written as ds dt. And then the acceleration function is a of t, and that's the second derivative of position, or the position of velocity, or I'm sorry, the derivative of velocity, so dv dt. And so this process of differentiation allows us to go from position to velocity to acceleration. What we want to do today is we want to explore how do you start with acceleration So we want to start with acceleration and work our way backwards to position. So we want to kind of go in the reverse direction here with this kind of problem. And so now what we want to do is go this direction. All right, so what we're going to do is we're going to start off with a function f of x equals x to the 6, something super, super, super simple. And so what we want to do is first make this definition. An antiderivative for this function is a function capital F of x where the derivative of capital F of x, where f prime of x, capital F prime of x is equal to little f of x. Right, so this function capital F of x, whatever it is, would be called an antiderivative for this for x to the 6th. And if you think about this for a second, you're looking for a function that when you differentiate it, you get x to the 6th. And if you think about the power rule, then you could, since this is just a x to a power, you could certainly reason that the power would have to be 1 more, because when you use the power rule with differentiation, you're going to be reducing the power by 1. And but then that gives you a constant of 7 in front when you use the power rule. So we put a 1/7 in front like that to cancel it out. And sure enough, you know, that would work, wouldn't it? If you take the derivative of f prime of x, whoops, you get 1/7 times 7x to the 6th, or you get our target function x to the 6th. And sure enough, then this function 1/7 x to the 7th is an antiderivative for the original function. All right, now is this the only antiderivative? Is this the only antiderivative for f of x equals x to the 6th? And the answer would be no, because you could certainly create other functions like capital F sub 1 would be 1/7 x to the 7th, maybe plus 2. Right? Because if you took the derivative of that function, certainly it would be the case that its derivative is also going to be x to the 6th, because the derivative of 2 is equal to 0. And going to the next screen, capital F sub 2 of x maybe is 1/7 x to the 7th minus 9. Certainly its derivative is going to be x to the 6th also. So these functions that I've written down, f of x, the first one, which was 1/7 x to the 7th, f sub 1 of x, which was 1/7 x to the 7th plus 2. The third one I wrote down, f sub 2 of x, which was 1/7 x to the 7th minus 9. These are all antiderivatives for our little f function x to the 6th, because every one of them has a derivative that's equal to x to the 6th. Right? Certainly f prime is equal to x to the 6th, f sub 1 prime is x to the 6th, and f sub 2 prime is x to the 6th. It's certainly reasonable, after looking at these couple of examples, that all the antiderivatives look like this. All the antiderivatives for little f of x equals x to the 6th look like this, basically. They all look like capital F of x equals 1/7 x to the 7th plus some constant right there. And so, and sure enough, they all do, Right? Every antiderivative for x to the sixth ends up being in that form right there. And so we call this this function in this form 1/7 x to the seventh plus c, where c is some arbitrary constant. So this is an arbitrary constant right here. We call this the family of antiderivatives. The family of antiderivatives for our function little f of x equals x to the sixth. Now the notation we're going to use for this, we're going to use a special notation for this. The notation is going to look like this. We're going to use what we call an integral symbol for our function x to the sixth dx, like that. That dx is a differential, but it's, in this case, right now, all you have to do is think about that as being the variable that we're integrating with respect to, or that it tells us what the independent variable is in the problem. And this is read the indefinite integral. This notation right here is called the indefinite integral. Of little f of x equals x to the sixth. Just in short, the indefinite integral. And this symbol right here is called an integral symbol. It's kind of an elongated S looking kind of shape. And it's called an integral symbol. And the dx is really, at this point, part of the notation, right? So you have the integral symbol with a function in these brackets, dx. The integral symbol and the dx kind of go together, and they tell you what the independent variable is that you're integrating with respect to here. And what does this notation represent? When you're looking at, for our function x to the sixth, it represents this family of antiderivatives. So we say that the indefinite integral of x to the sixth dx would be 1/7 x to the seventh plus c. And in general, this notation is the indefinite integral of the function of little f. And in general, this represents the family of antiderivatives for little f of x. All right, and we're going to go ahead and highlight that. That's an important idea right there. Remember, the name for that integral is called the indefinite integral. We're going to look at several types of integrals this semester. Calculus students are going to look at several different types, many more than just two. But for now, this is the indefinite integral. And this is the only one we're going to look at for right now. We'll look at a second type of integral later, in another day or two. And then later on, as a Cal 3 student, you look at still other types of integrals. Right, but this is called the indefinite integral right here. All right, so let's look at another problem now. So another example. Let's say we have the indefinite integral for x to the ninth dx. So what would this represent? This is the family of antiderivatives for little f of x equals x to the ninth. We're looking for functions with that when we differentiate them, we get x to the ninth. And what do we see here? That if you write capital F of x equals 1/10 x to the 10th, but sure enough, when you differentiate that function, capital F prime, you do get x to the ninth. All right, so the family of integrals, the family of antiderivatives, would be capital F of x equals 1/10 x to the 10th plus some arbitrary constant. And so we say that the indefinite integral for x to the 9th dx would be equal to 1/10 x to the 10th plus c. All right, so we can sort of start streamlining this process a little bit. Right, if we have the indefinite integral for x to the 3rd dx, we would see that we want to write the family of antiderivatives for x to the 3rd. And so that family of antiderivatives would take on this form, 1/4 x to the 4th, and then plus some arbitrary constant. Right? That, remember, it represents the family of antiderivatives, so that constant must be written in there. Very important in certain applications. Horrible habit to forget to write that plus c. And so I'm really going to get after you throughout the rest of these lectures, throughout the rest of the semester, about putting that arbitrary constant down whenever you're looking at an indefinite integral. All right, if we have x to the, let's say, 1/2 dx, maybe a little bit more difficult, but you should start seeing a pattern here, that the exponent on this x has always got to be one more when you're looking at an antiderivative. So if you take 1/2 plus 1, you get 3/2, right? That we're adding 1 to the exponent. And that notice that the constant coefficient of the x, because you want it to cancel out when you're differentiating, has always got to be the reciprocal. And so this would be 2/3 x to the 3/2 plus c right here would be our antiderivative. You could certainly differentiate that function to verify that its derivative, right? If you look at capital F of x equals 2/3 x to the 3/2 plus c, capital F prime, using the power rule, would be 2/3 times 3/2 times x to the 1/2. And what happens, the 2/3 and the 3/2 cancel each other out. You're just using the power rule for differentiation there. So you're bringing that 3/2 down in front. It cancels with the 2/3. When I say cancels, it multiplies to give you 1. And so sure enough, you're left with x to the 1/2 like that. All right, if we have a negative exponent, so x to the -5 dx. Right, so the same pattern continues to exist even for a negative exponent. If you add 1 to the exponent, you get x to the -4. You put the reciprocal of that exponent in front, -1/4, and then don't forget to add our arbitrary constant plus c. Once again, that's our antiderivative, our family of antiderivatives right here. We could verify that what we just wrote was correct by differentiating this function. So this -1/4 would come down for the ride, and we'd use the power rule on x to the -4, which would be -4 times x to the -5. The derivative of c, since it's a constant, would be 0. And what do you get? Sure enough, you just get x to the -5 right there. So this all works out really well. All right, so what we've seen here is that kind of in general, we can summarize these last problems by writing down this form, that x to the n dx, if you're looking for the antiderivative for x to the n dx, that would be equal to x to the n plus 1, that you add 1 to the exponent, that you put the reciprocal of the exponent in front. That's the way I will say it. So that's the reciprocal of the new exponent. And you're actually going to put that as a coefficient in front. And then don't forget the plus c, the arbitrary constant right there. This is sometimes called the power rule for anti-differentiation. Sometimes called the power rule for antiderivatives. Now notice that this power rule works out really well for every power except 1. So let's just look at another example or two. If we have the antiderivative for x to the 8th dx, then using this power rule, we would add 1 to the exponent, put the reciprocal of that exponent in front, and then add the arbitrary constant. So it works out pretty slick. If you have 1 over x to the 10th dx, the first thing you don't want to do when you write this power rule is you would want to write powers, everything as powers of x. So this would be x to the negative 10 dx first of all, and then you use the power rule. So you add 1 to the exponent, so that would be x to the negative 9. You put the reciprocal of that exponent, of that new exponent in front, so that would be negative 1/9, and then plus c. Usually we try to write these without negative exponents, and so I would write this as the negative of 1 over 9x to the 9th, like so. And then obviously plus the arbitrary constant c. If you have a radical, so the cube root of x dx, and you're looking at that indefinite integral, the first thing you'd want to do here is you'd want to rewrite this as a power. If you're going to use the power rule, you'd want to write everything as a power of x. So this would be x to the 1/3 dx. And then we can execute this power rule. So you add 1 to the exponent, which would be x to the 4/3, and you put 3/4 in front as it. And remember, that's the reciprocal of the new exponent. Remember, you're adding 1 to the exponent, so 1/3 plus 1 is 4/3. And so that's how I'm getting the 4/3 right there. Don't forget to add the arbitrary constant c. And even though the original function was written as a radical, it would be okay to write this just as a fractional exponent here at the end. That would not be too much of a problem. So this power rule, it can be used when you've got an x raised to a power. Now there is a power where this is not going to work. If you think about this for a second, if you look at the way this power rule is written, here's our power rule for antiderivatives. Here's the rule right here. But if you think about that 1 over n plus 1 that's written as a coefficient, you can clearly see that that n cannot be equal to negative 1 in this case, because if n was equal to negative 1, then you'd get division by 0 right there. And so n can't be negative 1. So let's explore that one for a minute. So if we have, let's look at one with a power of negative 1. So that'd be 1 over x dx. Right? And so 1 over x dx, that would be x to the negative 1 dx. And you can clearly see that this is not going to be the power rule. In fact, there is no power of x that has a derivative of x to the negative 1. If you think about how the power rule works for differentiation, not anti-differentiation, but differentiation, there's no way I could write a power function here whose derivative was x to the negative 1. Instead, we do know a function whose derivative, first of all, not the power rule. Not the power rule. And so what do we see? That the power rule does not work when you have a power of negative 1, right? And that's what we were talking about right here, that n cannot be negative 1. And so power rule does not work when that power is negative 1. Right, so let's look at a function whose derivative is 1 over x. So notice, and we do have a function like that, and that function is natural log of x, right? The natural log function, f of x equals ln x, its derivative is going to be 1 over x. So what can we see here? That the antiderivative for 1 over x is going to be the natural log of x plus an arbitrary constant. The other thing we have to be careful about here is that when you look at the function 1 over x, the x value can be negative, but the natural log of x, you can't take the log of a negative number. So what you have to use here are absolute values around that x to ensure that you're always taking the log of a positive number. And so we have our second rule for antiderivatives. And so this is our log rule for antiderivatives. Right, and so the log rule for antiderivatives is like we've got stated here, I'm going to go ahead and highlight this, that the integral for 1 over x dx is natural log of x plus c. Now that 1 over x dx can actually, you'll see that written in a couple of different ways. First of all, another way that you'll see this written is as dx over x. Those mean the same thing when you got 1 over x dx and dx over x. You'll frequently see it the second way. Either way, this is the natural log of the absolute value of x plus c. All right, and then you'll also see that this is going to come up in various problems that we're going to encounter as we look at combinations of these kinds of functions. And so we'll see that as we come up against those problems over the next few minutes. All right, so we have the log rule. So the next rule we want to look at is the constant factor rule for antiderivatives, the constant factor rule. And so what happens when you have a constant factor as part of your function? Right? That's what this rule is applying to. And you're looking for an antiderivative. So you're talking about a situation like this, where you're finding the antiderivative of some constant times f of x dx, like that. And the rule is pretty clear-cut. This is exactly like for derivatives and for limits, and that is that the constant can be brought outside the integral and does not affect how you write down the antiderivative at all. And so it's always okay to take that constant factor and write it outside of the integral. Okay, so how will that come up in our case? And it's going to come up just constantly for us in our future as calculus students. It's just going to come up over and over and over again. So it's going to come up in just a simple problem like this. So if we have 6x to the 4th dx, right, that 6 has nothing to do with the antiderivative for x to the 4th. It just gets multiplied by the 6, the antiderivative does at the end. So this is what the rule technically says you can do, is that you can just bring the 6 outside of the integral and then just find the antiderivative for x to the 4th. And so that's a power rule problem. That would be x to the 5th. You add 1 to the exponent. You put the reciprocal of the exponent in front, 1/5, and then plus our arbitrary constant. And so then you end up with 6/5 x to the 5th plus c. Right, so the 6 did not affect how we wrote down the antiderivative. All right, if we had -9 times x squared dx. So you think about the fact that the -9 does not affect how you differentiate, and so it certainly would be okay just to bring the -9 over and then just multiply that by the antiderivative for x squared. I add 1 to the exponent. I put the reciprocal in front, which is 1/3. I add the arbitrary constant in, and so that gives me -3x cubed plus c. Remember, you can always differentiate that answer. That when you differentiate that answer, you better come up with the original function. All right, from a practical standpoint, what most students end up doing, for example, this problem right here where we're looking for the antiderivative for 3/5 x to the 6th dx, most students are just going to say, okay, that 3/5 is going to come along for the ride. So I add 1 to the exponent. I get x to the 7th. I put the reciprocal in front, which is 1/7 times the 3/5, and I get 3/35 plus c. Now, if you want to, and definitely not a problem at all, especially at this early stage with antiderivatives, but if you'd rather not skip over all those steps, then please, by all means, then write this as 3/5 times, and then write the antiderivative for x to the 6th, which is 1/7 x to the 7th, and then plus our arbitrary constant, and then multiply everything out at the end. Like that. All right, however many steps you want to write in there, that is absolutely okay. All right, so that's our constant factor rule. The next rule we want to look at is the sum difference rule. for antiderivatives. So the sum difference rule, again, works very much and goes very much along the lines of the sum difference rule for derivatives and for limits also. And so the sum difference rule goes like this, that if you're looking at the antiderivative for f of x plus or minus g of x dx, like so. So if you're trying to find the antiderivative for a function that's written as an addition or subtraction problem, that this would be okay to look at the antiderivative for the first term plus or minus the antiderivative for the second term. You just differentiate, look at for the antiderivative term by term. So this is called the sum difference rule for antiderivatives. So as an example, we have 2x to the fourth plus 3x squared minus 8. And we want to look at the antiderivative for that function. And so first of all, since this is an addition and subtraction problem, this would be legal to go ahead and split this up like so. So technically using the properties, technically using the properties, this is what you're doing. You're taking the antiderivative for each one of these terms like this separately. And then using the constant factor rule, you're bringing the 2 out in front like this, the 3 out in front like this. And technically the 8, if you wanted to, you could bring that out front. You could treat it the same and just have a 1 dx there. That would be okay to do. And so what do you end up with here? You end up with 2 times 1/5 x to the 5th plus 3 times 1/3 x to the 3rd minus, okay, now that 8 is multiplied by the antiderivative for 1, and the function whose derivative is 1 is x. And if you think about it, that really is the power rule, because if it's x to the first, you subtract 1 from the exponent, and you do get x to the 0. So you are using the power rule here. And then plus c. And so you get 2/5 x to the 5th plus 3 times 1/3 is 1, so you just get x cubed minus 8x plus c. Some people and some textbooks will actually write the constant as a separate rule, and they'll talk about the antiderivative of a constant. And I'll actually write that out as a separate rule. And so they'll look at, and you'll see it written this way, that the antiderivative for c dx, let's make that constant a little bit different here. Let's say k dx would just be k times x plus an arbitrary constant. So the antiderivative for a constant is just the constant times x, is all we're saying right there. All right, so that works out really well. It's okay to find antiderivatives for addition or subtraction problems by just finding antiderivatives for each term separately. Constant factors don't affect anything, so this is all working out really, really well so far. Now that's going to stop very quickly, and we're going to see that anti-differentiation gets more difficult as you move into multiplication and division problems and composition functions. All right, so let's look at some more examples and kind of work through some basic things here, basic situations for anti-differentiation. So if we have, for example, 2x to the 4th minus 3 square root of x plus 5 over x cubed dx, and we're trying to write the antiderivative down for that function. So you want to rewrite, so you can use the power rule. So rewrite each term so power rule can be used. So the first term is fine like it is. That the power rule is okay in that one. The second term, I need to rewrite the radical as a power. So I rewrite that as 3x to the 1/2. Plus, and then the third term, the 5 over x cubed, I rewrite that as 5x to the -3. But I rewrite each term so I can use the power rule. All right, and now you use the power rule for each term. The constant factors just come down for the ride for each term. So in this first one, you have 2 times, and then this would be 1/5 x to the 5th, right? You add 1 to the exponent, put the reciprocal in front. Minus 3 times, add 1 to the exponent, x to the 3/2. Put the reciprocal of that exponent in front as a factor, 2/3. And then the next term, the 5 just comes along as a constant factor. I add 1 to the exponent, which is x to the -2. I need to put a little bit more room there. And then put the reciprocal in front. And that's just 1/2. And then that 1/2 is going to be negative, so that changes that term to a negative right there. And then plus c. So cleaning that function up a little bit, you get 2/5 x to the 5th minus 2x to the 3/2 minus 5/2 times 1 over x squared plus c. All right, that all looks good. Let's look at that log rule again. If you have the integral of, let's say, or the antiderivative for 3 over x dx, like so, that 3 is a constant factor, so it could be brought outside the integral. So you have 3 times the integral of 1 over x dx. And we've seen that the 1 over x dx is our log rule for antiderivatives. It's not a power rule problem. So be careful, not a power rule, because the power is x to the -1. Right? The power rule does not work for when the power is -1. It's the only power where it doesn't work. But what do you get instead? The antiderivative for 1 over x dx is just natural log of the absolute value of x plus c. All right, so that's a problem involving the log rule and also that constant factor rule right there. All right, let's look at a problem where algebra will help us out. So if we have the antiderivative for x to the 4th minus 2x cubed plus 6x minus 1 all over x squared dx. One thing is we have not talked about a quotient rule for antiderivatives, and the reason why is there is no quotient rule for antiderivatives. So let's go ahead and put this kind of in a different color here. No quotient rule for antiderivatives in general. So that's a huge difference between antidifferentiation and differentiation. With differentiation, if you had a fraction, the function was written as a fraction, you knew you could apply the quotient rule to differentiate that function. That does not work for antidifferentiation. So instead, what we have to do here is use algebra instead to write each term as the integral of x to the n dx. And then it's either the power rule or the log rule once you get it in that form. Right? And so that's what you're trying to use here, or trying to look at. So the algebra I can use here is I can divide, in this case, every term by x squared. Right? I can divide this out term by term. Like so. So I divided it out term by term. I'm using algebra to rewrite each term so it's in the form x to the n dx. So the first term would be x squared. Second term would be 2x. Third term would be 6 over x. And then the last term would be x to the -2. Now notice I did not write that third term as 6x to the negative 1 because I just left it as 6 over x because that's going to be the log rule, right? The n there is negative 1, and so this is a log rule problem. Right here, n is negative 2. That's a power rule. Right, you have the power rule for any other power besides negative 1. This is n equals 1, power rule. Finally, n equals 2, the very first term, n equals 2, also the power rule. Right, so the only power that you do not have the power rule is when the power is negative 1. In that case, you have the log rule. All right, so the antiderivative here would be 1/3 x to the third minus the exponent on that second term is x to the first, so you add 1, you get x squared. You put the reciprocal in front, which is 1/2, but there's a 2 out in front, so that's just a 1, so you end up with minus x squared. Then the 6 over x, well, the 6 is a constant, so it comes down for the ride, and the antiderivative for dx over x would be natural log of the absolute value of x. And then this last term, add 1 to the exponent, put the reciprocal of negative 1 in front, which is negative 1, and so you get a plus 1 right there. Then please don't forget the arbitrary constant at the end. So you end up with 1/3 x cubed minus x squared plus 6 natural log of the absolute value of x. Get rid of the negative exponent on that last term, write it as 1 over x, and then plus c. So algebra came to our rescue in this kind of problem. All right, this will be the same for this next problem. You have the antiderivative of 2x cubed minus 3 times 5x minus 1 dx. Now remember, in the last problem, we talked about the fact that there's no quotient rule for antiderivatives. Well, that's the same thing for the product rule. No product rule, not really, no product rule for antiderivatives. So if there's no product rule, then your only option when you have a multiplication problem, at least at this point, is to try to use algebra to your advantage. And in this problem, I can certainly do that. I can multiply this out using algebra and then find the antiderivative. So I just multiply this out using the FOIL method, and I get 10x to the fourth minus 2x cubed minus 15x plus 3. So I multiply this out. And now each one of those terms, first of all, I know I can find the antiderivative for each term separately. Each term is simply a power of x. The constant factors just come along for the ride. Right? So the first term, the antiderivative for x to the fourth, I raise the exponent by 1. I put the reciprocal in front, which is 1/5, times the 10 that's out there gives me a 2. You have 2x to the fifth. The next term, I add 1 to the exponent, I get x to the fourth. I put the reciprocal of that exponent in the front, which is 1/4, times the 2 that's already there, I get 1/2. The next term, I add 1 to the exponent, that's x squared. I put the reciprocal of that in the front as a factor. That 1/2 times the 15 that's already there gives me 15/2. Finally, we've seen that the antiderivative for a constant is just a constant times x, and then plus our arbitrary constant, and there's our antiderivative. Right? So we had to use algebra to multiply it out to get rid of the multiplication, and then we could find the antiderivative term by term. All right, so I think we're doing okay here. Let's look at, okay, so we've seen the most important rules here now are the power rule and the log rule. Those are the two. And then we've got addition and subtraction and constant factor. But we want to look at some other rules that are not, some other problems that are not the log rule or the power rule. So let's first look at the trig functions. So let me title this here. So trig functions and antiderivatives. Now remember, we know that the derivative, let's write the derivative forms down first. The derivative of sine x is cosine x, and the derivative of cosine x is negative sine x, and the derivative of tangent is the square of the secant, and the derivative of the secant is secant tangent. And then we also have the cotangent and the cosecant in there also, right? The derivative of the cotangent of x is negative cosecant squared. And finally, the derivative of the cosecant of x is negative cosecant x cotangent x. Those last two we just don't use nearly as much as the first four. So if you turn these forms around, you get our antiderivative forms for the trig functions. And so we get that the indefinite integral for cosine x is sine x plus an arbitrary constant. Don't forget the arbitrary constant. The antiderivative for sine x would be negative cosine x. And all you have to do is look at the derivative form right next to it to see why that would have to be true. The antiderivative for secant squared x would be tangent x plus c. The antiderivative for secant x tangent x dx would be secant x. And I'm just going to put, at this point, I'm just going to put etc. Because it would be the same thing for the cosecant and cosecant cotangent functions there. Notice that we do not have a form at this point. So, you know, some of those forms are clear-cut for cosine and for sine, but then you've got these special forms, the antiderivative for secant squared and the antiderivative for secant tangent. And so the question is, what about the derivative of the tangent and the derivative of the secant as examples, or the antiderivative? So the antiderivative for the tangent and the antiderivative for the secant, these are for later in the semester. We are not ready to tackle this just yet. So for later in the semester. So we will get to those, but we are not ready to do those and put those in as forms just yet. So we're not ready to tackle that. So as an example then, let's look at what we've got here. So some examples. If you have, for example, 5 sine x minus 6 cosine x minus x cubed dx. So this would just be a subtraction problem. So I know I can find the antiderivatives term by term. The constant factors just come along for the ride. So in this first term, this is, this first term, this is 5 times the antiderivative for the sine, which is negative cosine. Remember, this is an antiderivative. Minus 6 times the antiderivative for cosine, which is positive sine. And then the last term is a power rule. So that would be x to the 4th and then a 1/4 in front. And then finally plus c. So our antiderivative would be negative 5 cosine x minus 6 sine x minus 1/4 x to the 4th plus c, like so. Okay, so we're doing good here. So if we look at an antiderivative, for example, if you have secant x times secant x minus cosine x dx, like this. So remember, there is no product rule that we have available to us at all. So I need to write that down again. No product rule. So when I see a multiplication problem right now, my only option for the most part at this point is to try to multiply it out and see what I can do with it. We will look at other options that we have later in the semester. for now, all I'm going to do is multiply this out. So use algebra right here. So when I use algebra and multiply this out, I get secant squared x minus secant x cosine x dx, like so. And so you get secant squared x minus, and then secant times cosine. Well, secant and cosine are reciprocals of each other, so that's just minus 1 dx, like this. So now I've got secant squared x minus 1. And so is there anything I can do here to find the antiderivative? Well, secant squared minus 1, the antiderivative for secant squared is tangent, right? And so using that idea, then I could write this as tangent x minus x, like so. Right, and then that would be plus an arbitrary constant c. Okay, so we're doing good. We're doing good. So let's look at exponential functions. So we're kind of going through a little survey of all the different functions that we've talked about so far and their antiderivatives. So with exponential functions, in particular base e exponential functions, we've seen that the derivative of e to the x is equal to e to the x. So if you turn that form around to make it an antiderivative form, notice that you get then that the antiderivative for e to the x dx would be e to the x plus an arbitrary constant. So that works out pretty well. Now, we could also extend this a little bit, which I think would be worth it. And maybe we might even look at some trig functions and go back and look at those also. But the derivative, what's the derivative of e to the 3x? Well, that's 3e to the 3x, right? 3e to the 3x. And in general, the derivative of e to the bx, or b is just some real number constant there, would be b e to the bx, right? Because that's a chain rule problem in both cases. The derivative of 3x is 3. Derivative of bx would be b. So now how could we take advantage of that, what's going on there, to find the antiderivative for e to the bx power? Well, say so if you're looking for a function that when you differentiate it, right, gives you e to the bx, but what do we know? That if you just write e to the bx, its antiderivative, its derivative rather, is b e to the bx. So if you're kind of going backwards here, you're going to get b e to the bx, right? And so what do we need there to cancel out that b? Well, we need a 1 over b. You have 1 over b e to the bx plus c, like so. Right? And sure enough, if that is your antiderivative, capital F of x is 1 over b e to the bx plus an arbitrary constant, and certainly its derivative, what happens? The 1 over b comes down for the ride, and then the derivative of e to the bx is b e to the bx. The derivative of c is 0. And what happens? The b's divide out, and you're left with e to the bx, which is what we needed. So that's a little bit more general of a statement, and that's what we need here. So the exponential functions, the rules for antiderivatives, rules for antidifferentiation, right, I'm going to go ahead and highlight that. And really, this is our rule right here, that when we take the antiderivative for e to the bx, we get 1 over b e to the bx plus an arbitrary constant. So if we have, as an example, we have the antiderivative for e to the 6x dx, then the antiderivative for that would be 1/6 e to the 6x plus c. The antiderivative for e to the 1/2 x dx. So remember, what are you doing there? You're putting the reciprocal of that constant in front as a factor. So in the first problem, the reciprocal of 6 was 1/6. So the reciprocal of 1/2 would be 2. So this would be 2 e to the 1/2 x plus c. Remember, you can always differentiate your answer and make sure that you get the original function back. Right? And that 2 and that 1/2 will cancel each other out when you differentiate. The antiderivative for e to the negative x dx. Notice then that when you have a negative sign there, all that does is change the sign when you're finding the antiderivative, because the reciprocal of -1 would be -1. So this would be negative e to the negative x plus c. All right, so kind of combining those ideas in one problem here. You have the antiderivative for e to the 3x minus e to the negative 3x dx. Antiderivatives for functions like this are not uncommon at all to encounter in applications. So the antiderivative for e to the 3x would be 1/3 e to the 3x. The antiderivative for e to the negative 3x, you'd have e to the negative 3x, but you'd have a negative 1/3 in front. But there was already a negative sign there, so that changes the sign to plus 1/3 e to the negative 3x plus c. And so you've got the antiderivative for that exponential function there. So now, more complicated exponential functions, we'll have to save that for later. All right, so now we've seen, so let's go back to sine and cosine for a minute. We have written down now that the antiderivative for sine x dx is negative cosine x plus c, and the antiderivative for cosine x is sine x plus c, like that. So what happens if you've got the antiderivative for sine of 3x, right? Or the cosine of 5x, or something like that? So again, think about differentiation in a problem like this. Think about differentiation. And so the derivative of the sine of 3x, using the chain rule, is the cosine of 3x times 3, right? The derivative of the inside function, which is 3. So you have 3 cosine 3x. And so what's going to happen with the antiderivatives, you're going to have to somehow cancel that 3 out, and so you need the reciprocal. And so with antiderivatives, first of all, the antiderivative for sine is negative cosine, so this will be the negative cosine of 3x. And then you will need the 1/3, and we usually write that 1/3 in front as a factor. So now be careful that negative sign goes with the cosine as a factor there, and then plus c. So you end up with negative 1/3 cosine of 3x plus c. So let's check that out. Let's take the derivative. So here's my antiderivative. That capital F of x is negative 1/3 times cosine of 3x plus c. So the derivative of that function, well, the negative 1/3 comes along for the ride. And then using the chain rule, the derivative of the cosine is negative sine. So you have negative sine of 3x, and then times the derivative of the inside, which would be times 3. And notice what happens. The negative times the negative is a positive, and then the 3 times the 1/3 is a 1. And so sure enough, you're left with sine of 3x. Right? That was the original function. That's what we were looking for. So we could kind of summarize this idea also and write those out kind of as rules in some ways, is that if you have the sine of ax dx, if that's the antiderivative you're looking for, then this would be negative 1 over a cosine of ax plus c. And the antiderivative for cosine of ax dx, same thing, would be the antiderivative for cosine is positive sine, and then you have the 1 over a there as a factor. So you have 1 over a sine of ax plus c, like that. Right, so those are nice little rules to know for antiderivatives that will be helpful. And it makes sense, if you think about it this way, that the derivative of functions like this just gives you that constant factor in front. So it makes sense because of the chain rule. So it makes sense that when you look at antiderivatives, you're looking at the reciprocal of that constant sitting in front. And this would be the same for the other trig forms that we've already written down. There wouldn't be any difference. I'm just going to write the sine and the cosine, but there wouldn't be any other difference there. All right, so we're going through, and we've looked at power functions now. We've looked at in the power rule. All right, and so we've got the power rule. We've looked at the, this is when the power is not negative 1. We've seen when the power is negative 1, we get the log rule, like so. Right? We have trig functions now. So we've taken care of those types of functions. We've looked at exponential functions. And so we have those types taken care of. And so the last type of function that we want to talk about, that we've already talked about as far as derivatives go, are the inverse trig functions. Inverse trig are the last ones to go here. So these are next. So if we look at and go back and kind of recall that the derivative of the arc sine of x is, arc sine of x is 1 over the square root of 1 minus x squared, right? And the derivative of the arc tangent of x is 1 over 1 plus x squared. And the derivative of arc secant is 1 over x times the square root of x squared minus 1. We can get by with just those three properties and look at antiderivatives. We don't need the arc cosine and the arc cotangent and the arc cosecant, as it turns out, because of the negative signs in front just come outside in front of the integral. So we never need those other forms, which is great. So here then, with antiderivative forms, for inverse trig functions, all right, so we would be looking at the antiderivative, for example, of this form, 1 over the square root of 1 minus x squared dx. That form, you're going to get arc sine x plus c. The antiderivative of 1 over 1 plus x squared dx is arctangent of x plus c. And then finally, the antiderivative for 1 over x times the square root of x squared minus 1 dx is arcsecant. Now we're going to look at more complicated forms involving the inverse trig functions, but we're not going to do that now. We'll kind of gradually introduce those over the next week or two. So we're just going to kind of stick with these basic forms right here. So if we have this problem right here, let's say we have 3 over 1 plus x squared minus x to the fourth, this kind of a weird function, minus e to the 2x plus 1 over x dx. This involves most of the functions that we've talked about. So you're just looking at the antiderivative term by term. right? So that 3 doesn't affect anything in that first term. So you have 3 times the antiderivative of 1 over 1 plus x squared dx. And so that matches up with the arctangent. This next term is going to be a power rule. This next term is going to be the exponent function rule that we've talked about. And then the last rule, this is when the power is n equals 1. And so this is going to be our log rule problem right here. So the antiderivative here would be 3 arctan x minus, and then the power rule on this second term would be 1/5 x to the 5th. Right, the antiderivative for e to the 2x. We've seen that the antiderivative here would give you a constant factor of 1/2 times e to the 2x. And then finally our log rule, so this would be the natural log of the absolute value of x plus c. Whew. So that's a kind of a messy, kind of complicated problem there, really. But all you're doing is learning how to apply the rules for these various different antiderivatives that we're talking about here. All right. So we've got a couple of more situations to look at. We're done with the rules that we're going to talk about, but there's a couple of other situations that we want to deal with here. All right. So the first thing is, if we have a function like this, let's say we're given a function and we're given that the second derivative of a function is equal to x squared. Right? And we're also given that f prime of 0 is equal to 8. And we're given that f of 0 is equal to 4. These are sometimes called initial conditions. So let's say we have some function f, but we know its second derivative is x squared. We know its first derivative evaluated 0 is 8. The function itself evaluated 0 is 4. And the instructions here would be to find the original function. Find the original function. So to find the original function f. So to find the original function, we deal with the antiderivatives here. So if you find the antiderivative here for f double prime, then the antiderivative for f double prime is f prime. And so f prime would be equal to 1/3 x cubed plus some arbitrary constant. Right? So what do we do? We took our function f double prime, we found its antiderivative, and that would have to be f prime, because we know the derivative of f prime would be f double prime. All right, and then if we find the antiderivative again, we get f. So the antiderivative for 1/3 x cubed plus c would be 1/12 x to the 4th. Remember, you add 1 to the exponent, put the reciprocal in front. So add 1 to 3 and you get 4. Put the reciprocal of 4, which is 1/4 in front, times the 1/3 would give us 1/12. Plus the antiderivative for a constant, right? We've seen that the antiderivative for a constant is just the constant times x. This is cx. And then there has to be another arbitrary constant here at the end. So we put a plus k at the end here. So we end up with 2 arbitrary constants in this problem. And to find those, we could actually go ahead and use our initial conditions. We know that f prime of x is 1/3 x cubed plus c. We know that f prime of 0 is equal to 8. But f prime of 0, we also know from our function, is going to be 1/3 times 0 plus c, or just c. And so what's got to be true here? That c, take those two statements together, c has got to be equal to 8. And so in our last function there, we've got f of x is 1/12 x to the 4th plus 8x plus k. And then we can use the fact that f of 0 is equal to 4. So if f of 0 is 4, well, I know that f of 0 would be 1/12 times 0 plus 8 times 0 plus k. And so notice that's just k. Then what's got to be, take those two statements and put them together, and what do you get? That k has got to be 4. And I was able to use those initial conditions to actually find those arbitrary constants. And so our function becomes 1/12 x to the 4th plus 8x plus 4. And there's our original function. All right, and so let's see. Let's look at a situation where you have vertical motion. So let's look at vertical motion here. So when you have vertical motion, the acceleration of gravity, and the acceleration of gravity is negative 9.8 meters per square second. Remember, acceleration is negative 9.8 meters per second or meters per square second. So notice now I can use anti-differentiation to work my way backwards in a vertical motion problem and actually find the position function. So what I want to do here is find position using anti-differentiation. So to find position, we first use the antiderivative here of acceleration, and the antiderivative for acceleration is velocity. And so you get negative 9.8 t plus c. Now notice what that c has got to be here, that arbitrary constant. If I look at the initial velocity, which is the velocity at time 0, notice that's negative 9.8 times 0 plus c, and you get that v of 0 has got to be equal to c. So that arbitrary constant actually is just the velocity at time 0. So we could write it out that way, that v of t is negative 9.8 t plus v sub 0. All right, and then find the antiderivative again, and that would give us position. So position would be, using the power rule for antiderivatives, this would be t squared. Make that a little bit neater here. So that would be t squared, and then put the reciprocal in front, which is 1/2, times that negative 9.8 would give me negative 4.9. T squared plus, now remember v of 0 is a constant, that's just the velocity at time 0, so this would be v of 0 times t, and then this would be plus still another arbitrary constant c sub 1. But notice s of 0, the position at time 0, ends up giving you just c1. All the other terms go to 0. And so that second arbitrary constant ends up being the position at time 0. And so you end up with this position function that we've derived in a vertical motion problem. You get negative 4.9 t squared plus v of 0 t plus s of 0. V of 0 is the initial velocity. S of 0 is the initial position. And what do? We started, this is a vertical motion problem. We started with the acceleration to be negative 9.8, which is a known quantity. And then we were able to take that information and use anti-differentiation to derive the equation or the function that would give us position. All right, so what I want to do here now is I want to finish this discussion out by just kind of going back and summarizing the integration that we've talked about so far. So the summary of antiderivatives, of anti-differentiation. So what are we saying that the, whoops, let me write that better here. The antiderivative for a constant function is just that constant times x plus c. We've got the sum difference rule. And the sum difference rule tells us that when you integrate f of x plus or minus g of x, that's legal, right, to find the antiderivative for each of those terms separately. So we just do that just over and over and over again, just as a matter of course. We never even really think too much about it. We have the constant factor rule. That if you have the integral of a constant times some function, and so a constant factor means multiplication, that constant can be taken outside of the integral. We have the power rule, one of the biggies, right? The power rule says that x to the n dx, its antiderivative would be 1 over n plus 1, x to the n plus 1 plus c. And remember, this rule does not work when n is negative 1. And then we got kind of the companion rule, which is the log rule, and that is when n is equal to negative 1. And when n is equal to negative 1, right, we get this antiderivative form, that the antiderivative for 1 over x dx is natural log of the absolute value of x plus c. We have the exponential function rule. And that goes like this, that e, the antiderivative for e to the bx dx is equal to 1 over b e to the bx plus c. And then we have the trig rules. In particular, we have that the antiderivative for sine of ax dx is the negative of 1 over a cosine of ax plus c. And for cosine of ax, we get 1 over a sine of ax plus c. And then remember, you have the other kind of special rules for the trig functions right now, which are that the antiderivative for the tangent for secant squared rather is tangent, and the antiderivative for secant tangent is secant. And then you have a few other rules for the trig rules. And then finally, we have the inverse trig rules. And the inverse trig rules are that you have dx over the square root of 1 minus x squared, or you'll see this written as 1 over the square root of 1 minus x squared dx. You see it written both ways. Those are equivalent statements. And that'll be arc sine x plus c, that's the antiderivative. Then we have the dx over 1 plus x squared, or 1 over 1 plus x squared dx, and that's arc tangent. Whew. And then finally, the last one, dx over x times the square root of x squared minus 1 is equal to, let's see, 1 over x times the square root of x squared minus 1 dx. Those are the same form, and that's arc secant. To learn these rules, what you got to do is you got to practice, practice, practice. So I'm going to write that 3 times. Practice, practice, practice. I'm going to give you some more practice problems gradually over the next few days, not just what's out of textbook homework, but some other problems to help you practice and get through some of these forms so that you can start getting used to these. So, okay, so that's it for the day. Remember that your homework is on section, or homework that's due, homework 4 that's due is due on Wednesday in sections 4.3, 4.5, and 4.6. So please get that finished up and get turned in. I'm afraid some of you have gotten pretty far behind on your textbook homework. So I'm going to try to remind you again using some emails over the next day or two. And then we're going to move on to homework 5 and homework 6 and try to finish up the semester. We have about a month left. Thanksgiving's in there, so we really only have 3 or 4 weeks left of class. So it's really winding down pretty quickly. Have a great day, and I will be in touch. Please come by my online office hours. I will be happy, very happy to help you out. So please don't hesitate to come by for help. Thank you.